Very good. So let's start our afternoon session, and we're very happy to have Paolo Aluffi talk to us about characteristic classes in intersection theory.
Thank you. Thank you very much for the invitation. I confess it's my first time in Padua, although I was born and raised in Italy. And it's a really nice town. I enjoy it a lot and I enjoy the conference. I should confess that I've never computed an amplitude in my life. And that's confession number one. Confession number two is that actually the intersection theory I do is not intersection theory you do. So somehow, I guess that's why I'm here. I try to maybe say a few words about intersection theory, the other side of the force, the other side of intersection theory. And my main message will precisely be that there exists such a thing. Yeah, this is my plan. I guess I'm supposed to look at this, right? No, this is more of a colloquium than a research seminar. I will try to give a little bit of the background of intersection theory in algebraic geometry, the way I'm familiar with. And then I will focus on a little corner of that, which is the theory of characteristic classes for singular non-compact algebraic varieties. This should allow me to, so let me stress the non-compact part. That's maybe a little bit of interest to you, since you are computing order characteristics of complements of things. Those are non-compact usually, and this theory is adapted to do that reasonably well. And then these classes will be called CSM classes. When the time comes, you'll see why. And I'll say a few words about these classes for the graph hypersurfaces defined by Zemantic polynomials. Okay, that's the plan. And the main message is that there exists a theory called intersection theory, and it has a distinguished history. I will try to kind of give you a little flavor of that. And of course, the obvious question is whether there is a relation between the intersection theory that we do in conventional algebraic geometry and intersection theory that is of use to you. So maybe the main question here is how can I help if there's anything I can do. Okay, that's the plan. I have to also confess that I'm very sleepy. By a rough count, I crossed the Atlantic 200 times, and it doesn't get any easier somehow. The jet lag is a tricky business. So I hope not to fall asleep during the talk. And I've actually been at the talk where the speaker fell asleep. Bianca was kind of famous for doing that. I've witnessed myself. I hope not. By standing, maybe I will not fall asleep. So this is a bit of a history, and it's totally laughable. First of all, it's subjective because it's not the way I view it, and in any case, no, it's 1% of 1% of the real thing. So this goes back to really ancient questions. Algebraic geometry is famous for going back thousands of years, and things that you can recognize as something that sounds like intersection theory is this problem. Apollonius, you may be familiar with this guy. Now, how many circles are tangent to 3 given circles? The answer is 8, and he was able to do a nice construction of that. So answering such questions nowadays would be done with intersection theory. So fast forward to the 1750s, you get the first instance of Bézout's theorem, which is really intersection theory in projective space, and that requires an awareness for what intersection numbers are, what intersection multiplicities are. So although it's hundreds of years ago, still you can see that the people were getting fairly sophisticated about this. And in fact, if you go forward a little bit, just a little more than 100 years, you get to Schubert, Hermann Schubert, which at the age of 29 wrote a fantastic book by the title of, what's the title? Does anybody know? Calcul der Abzählender Geometrie or something like that. Right? So something summarizing, among other things, what is now called the Schubert calculus, which is really intersection theory in Grassmannians and beyond. And if you read the book, you will find answers to hundreds of questions in what we call enumerative geometry. You do intersection numbers, we do intersection numbers. Enumerative geometry is computations of numbers. For example, this is a typical question would be how many smooth plane cubic curves in complex projective plane are tangent to 9 lines in general positions. What's the number? Well, in 1872, a very young guy in his thesis proved that there's 33,616. So we are in 1872, which is kind of way back. We cannot read that paper. It's a sequence of 3 or 4 short papers in Canton and by modern standards, you cannot really make sense of what it says. It would be an excellent project for someone in history of mathematics to figure out what Mr. Maillard was doing in 1872. There was a whole technology that Schubert had talked about and had developed, been developed in the previous decades, using some principle conservation of numbers, things that these people could handle extremely well and seemed extremely reasonable and were absolutely not rigorous. And in fact, just a little further, Hilbert in 1900, as one of his famous problems, asked to put enumerative geometry on solid grounds, make computations in enumerative geometry rigorous. But he is not. Hilbert's 15th problem was essentially asking to develop intersection theory, make it a rigorous part of mathematics. And in the 20th century, this was attempted at various levels of rigor. Of course, you all know the history of algebraic geometry, and it was guided in the first half of the 20th century by people who understood extremely well what they were doing, but again, by our standards, they were not really working rigorously. So many names can be associated with this kind of efforts. Weil, of course, is super rigorous, but Severi would not. Samuel Seger. Weil was the first person who really put on firm grounds the notion of intersection multiplicity. Samuel did similar work. Chow in the 50s proved a moving lemma, which, if you are coming from homology/cohomology, you think that that should be an extremely natural thing. If you want to intersect 2 objects and they don't intersect nicely, just move one of them so that they intersect nicely, and then do the intersection, and that defines your intersection theory. Why can't we do that? In algebraic geometry, you don't have so much freedom in moving things. Algebraic geometry is very rigid. You can only move things in their, what we call now the rational equivalence class. It's very hard to prove anything about it. So this is a big theorem. The moving lemma is an absolutely non-trivial statement. And indeed, honestly, I don't know the status of this in terms of what we call rigorous mathematics now, because I'm not talking about now 50 or 60 years ago. I'm just talking about 4 or 5 years ago. Joe Harris and David Eisenberg were writing a book in intersection theory. Oh, I should have put this on a slide. It's a beautiful book. It has a beautiful title. Are you familiar with this? The title of the book is this. So if you Google Harris 3264, you may find the PDF of the book still available. Obvious question. What is 3264, right? It's the number of conics tangent to 5 conics in general position. So Joe Harris, as you might know, is an extremely strong algebraic geometer, descending from these people, Severi, Zariski, Harris. There's a continuous line between that kind of intuition and his intuition, and one of his tasks in writing this book was to provide an elementary proof of the moving lemma, and he couldn't. And if Joe Harris cannot, in 2015, prove the moving lemma by elementary means, that means it cannot be proved by elementary means. So at some point, people realized that they had to move away from that kind of very geometric thinking, and they had to get into the thick of things. Grothendieck, of course, gave a tremendous contribution. Riemann Roch was what he gave his fields matter and his theory in intersection theory. But the real foundations was really carried out by Fulton and McPherson in the 70s, bordering into the 80s. There's this Bible of intersection theory. From my point of view, it's Fulton's intersection theory that was published in, I think, 1984. And this is completely rigorous. In fact, the only reasonable proof of the moving lemma we know is through the theory of Fulton-McPherson, which is absolutely not in the same spirit as Chow was working. So, of course, it's a very well-developed in general theory, but in particular, we know that every algebraic scheme has a Chow group, and you should think of that as homology in intersection theory, in algebraic geometry. It feels like that. It's a covariant functor. It moves nicely across proper maps. And if you are non-singular, if your variety is non-singular, then this group has a well-defined intersection product, which makes it into something that looks like cohomology. And there are many situations, Grassmannian's projective space made more, in which cohomology and Chow are I mean, homology and Chow are the same theory. So in this talk, I will really not talk about Chow at all, Chow group, because I think it will not add anything to what I'm going to say. Yeah, I had a couple of remarks. I mean, if you think, no, how can you do this? And you are familiar with intersection theory the way I've seen in this meeting, and then you probably think there must be some clever way of putting differential forms together to obtain numbers or intersections. And that's not the case. Differential forms are not part of the theory. As I mentioned, Chow's moving lemma is also not an ingredient in the Fulton-McPherson. And the Chow group is actually not for special varieties, maybe not for the varieties you may care about, but it is in general tremendously finer than homology. For example, oh, this is a terrible mistake, right? Let's see. Oh, so what's a good example? Elliptic curves. No, if you look at dimension 0 or an elliptic curve, no, H0 is not very interesting because they are connected, while the Chow group is tremendously big. It's uncountably generated. No? So you see, it's a very, very fine theory, but again, in this talk, that will not really play a role. But just to stress that there are substantial differences between what Fulton and McPherson did in developing intersection theory and what you might be used to think in terms of the calculus superform. I think I had a nice, yes. So I will just mention what the ingredients are. And this is a typical situation in Fulton-McPherson intersection theory. Cycle just means take subvarieties. You have two subvarieties in a variety V. I'm not asking V to be non-singular, but I'm asking the first of the two subvarieties to be nicely embedded in V, which means it has a nice normal bundle. No, locally, it's given as a complete intersection, something like that. While I put no requirement on Y. And then I do something magical. I don't move anything, but I deform things. I deform the embedding of, I probably should not even attempt to do this, but if this is V and this is X, X is nicely embedded, Y may not be so nicely embedded, who knows. I deform the situation to the situation in which V is replaced by the normal bundle, so something very straight of X and V. X is replaced by the zero section, and Y is replaced by a cone, which in this picture might look like this. There's a deformation that takes you from here to there, and Fulton exploits it to reduce this intersection problem to an intersection problem like this. And this is very standard. Normal bundles are nice. I mean, the vector bundles are nice. Zero sections are super nice in vector bundles, and cones are, to some extent, under control. Once you do that, now as my slide doesn't promise, oh, I see. Please go back to the slide. There you go. As in my slides, you can see this deformation. Yeah, these are the ingredients. What you get is a problem that you can study on its own, and your intersection product will be a suitable cocktail of Chern classes and Segre classes. I'm emphasizing Segre because that's something I care tremendously much about. In any concrete problem I've encountered myself, the Chern class was never a problem. But the Segre class, which is what takes care of this cone, that is super subtle. And I keep trying to find ways to make computation of Segre classes more reasonable. But that's a different talk. Okay, so if you have this, then all expected probability of the intersection theory, that as you might expect from your experience with intersection theory, can be proven from these definitions. So for example, the 33,616 cubics turned out to be indeed 33,616. That's my PhD thesis, as it happens. It was done exactly at the same time by Kleiman and Spicer too. And many, many more innovative questions were answered. In the 90s, there was a very substantial application of this theory to modular spaces, and this was mentioned already today, and probably yesterday, so this will not tell you much that you may not be familiar with. There's something called Faber's conjecture. Faber is Karl Faber, and now he works in Utrecht. On the tautological ring, that's a ring associated with the Chow ring of modular space, genus G curves, and punctures, and parts of them are still open. And they are extremely subtle. In fact, if you try to generalize them a little bit, you get wrong statements and all sorts of Lassi's in the audience and is in Padua, so that's whom you should ask to talk about these things. I'm definitely not an expert, but she is. Again, in the 90s, Witten's conjectures on intersection numbers of the modular space were proven by Kontsevich, and that's, I think, the main motivation for Kontsevich fields Mellor. By the way, yes, as I was reading a little bit of the papers that you people write, I run into interest in M0, and well, Sean Keel, a student of Fulton, has a very nice paper on intersection theory of M0 and bar. So if you're familiar with it, excellent. If you're not, you may want to look into it. It's in the transactions, you can find it very easily. There's a very nice paper by Malin, dating back to '94, called Generating Functions in Algebraic Geometry, and among other things, you get Betti numbers for M0 and bar. There's nice generating functions for the kind of things. I'm just implying that there was a lot of activity in this field in the 90s. In fact, there was this tremendous surprise for mathematicians, and this was mentioned today, this morning, at the Yanko, right? A computation by Candelas, Delos, Green, and Parkus of the number of cubics in the quintic threefold, exactly at the same time when Ellingshausen and Strömer were doing it in mathematics, and the two numbers were not the same. No, and this is like 25 years ago. So I can tell you that the mathematicians were saying, these physicists, okay, how can they possibly imagine they compute with it? They don't get our number, they are wrong, right? And of course, the physicists were right. It was kind of embarrassing, but and not only that. I mean, mathematicians could produce the number of lines of conics and after some corrections of cubics, and that was it. The physicists would give this generating series in which the coefficient of q to the 100 would be the number of degree 100 curves indeed. So it was clear that the physicists had something to teach to the mathematicians, and that down the road became, this is a gross oversimplification, quantum cohomology. And there are names associated with that, Fulton again, Pandaripanda. Graeber, who's visiting Padua this semester, so again, if you want to hear about this, invite Tom Graeber to talk to you. Okonkov, Deren, Fanteki, there's many more, of course. And then there are developments. Intersection theory is now done in stacks. There's equivariant intersection theory. I want to mention this because some computations in equivariant intersection theory look a lot like the kind of computations I've seen you talk about. Typically, you have a group acting on a variety. You want to compute, for example, a Chern class or some kind of intersection theoretic object. And the action of the group allows you to localize this so that you look at the fixed points of the action. Each fixed point will give a contribution. If you do explicit computation, these contributions will be nice, complicated rational functions, and then magically, once you put them together, you get a very neat answer. And doesn't that sound familiar? I mean, I've seen this happen in your talks. So I'm suggesting that there may be a connection there. And more, I mean, this is also connected with physics, Thomas invariance, Schubert calculus as a modern version. And then in red, because that's the next topic, among other things, people have thought about characteristic classes for singular varieties, and that's what I want to talk about next. Any question? Any complaints? Yes. So in fact, if you're intersection theory, I claim, is a field. It has an item in the mathematical reviews. And if you Google that, you get about 1,000 papers. At any given time, there's about 30 papers pending. So it is a rather, maybe not super big, but rather active subfield of algebraic geometry. Okay, so this is one topic that I just personally care a lot about. And again, I like to give some names. This goes back to something that Lee and Grothendieck proposed back in the 60s, that Maria and Schwartz did in the 60s. And then there are more names: Mather, McPherson, Fulton again, Johnson, Brasselet, Yokura. That takes you to the 80s. I did work on this since the 90s, so did Parzinski, Pragas, Sherman. Many names can be associated with this. I don't know if any of them sound familiar to you. So the prototype is the observation that vector bundles have Chern classes, and another gross oversimplification, but the ith Chern class of E is the obstruction to finding a certain number of linearly independent global sections in the bundle. Or if you want, I mean, the one I will care about is for a smooth, compact variety, you have the tangent bundle, and I want to consider the total Chern class, the sum of those CIs, for this particular bundle. So the components of this class tells you how far you are from defining global frames of vector fields in B. And by the way, you could talk about the cotangent bundle instead of the tangent bundle. That will not make any difference. It's obstruction to find the linear independent differential forms on your variety. So this is has been around for a long time. It's very well studied, and it's an important invariant. For example, the degree 0, the dimension 0 part of this class is the Euler characteristic. It's the obstruction to finding a non-vanishing vector field. That's due to Poincaré-Hopf, the Euler characteristic. Other things that you can see from the Chern class, for example, you can tell whether your variety is a Calabi-Yau by looking at the first component of this class, because it's negative the canonical bundle. Poincaré-Hopf, I mentioned, is the fact that the degree by this integral, I don't really mean an integral, but I mean picking up the degree of the zero-dimensional class in the class I'm writing over here. That is the topological Euler characteristic, which apparently people care about. So the question that goes floating around is, what is the right analog of this class? But if you give up the non-singular / compact assumption, what if your variety is singular? What if it is non-compact? Can you still come up with some kind of invariant that will have the same type of information? So for example, M0n, does it have some kind of total Chern class? So the first time I looked at this, there was a naive answer still. No, you can just, if your variety is singular, well, instead of the tangent bundle, use something else. Use some kind of naturally defined bundle. For example, the sheaf of differential forms is defined for every scheme. Can't I use that to define a class like this? And the short answer is that you cannot do that, or at least it doesn't really lead to a good theory. Korean sheaves, which is what omega 1 would be in general, don't really have Chern classes, and there are ways to fix that, and it leads to important classes called Chern Mather classes. But it doesn't quite do what I need to do. For example, in the non-compact case, I would lose too much information. I would not be able to extract the Euler characteristic from this class. So we're not going to do this. We need something a little less naive. And by the way, my time is running, but I want to mention that again, as physicists, you probably are very familiar with this, more familiar than I. There was a proposal for Euler numbers of quotients, varieties with all different singularities. This was proposed more than 30 years ago by Dixon, Harvey, Buff, and Witten. Batilev generalized this to a notion of stringy Euler number, and that has a Chern class associated with it. So there is a class whose degree is the stringy Euler number, just in case you run into that. That's an interesting story, but it's not what I want to do, because again, I want to focus a little bit on something that will give me information even if it is not compact, and that class doesn't do it. So let me describe something that is more than 50 years old, but somehow it's not as famous as it should be, I believe. It's an idea that goes back to Grothendieck. There's an interesting history about it, but this is not the place for that. And it requires a bit of machinery. So, as they say at the dentist, this will cause a little bit of discomfort, maybe if you're not used to thinking in these terms. But so take a group, the group of integer-valued constructible functions. So those are things that you can write as a sum of indicator functions, a function 1 that is 1 if you are on W, if you follow the notation, and it's 0 if you're not on W. And just take arbitrary linear combination of those with integer coefficients. Okay, finite linear combinations. So this may not look like a very interesting object, because it's just taking some varieties, giving them some weights, possibly negative, possibly positive. So if you're used to thinking in a certain way, it's just a group of cycles, algebraic cycles on B. But I'm going to do something that is not directly related with cycles, and that is I'm going to make a functor out of that in what might seem an unusual way. And notice I restrict myself to complex projective varieties, so I'm allowed to use things like the topological Euler characteristic. Let me tell you what happens if you have a proper map from a variety to another. I claim that you get a push forward at the level of constructible functions. And how do you define that? Well, generators here are indicator functions for subvarieties, so I pick a subvariety of x. And the result should be a function of y, so I pick a point of y, and I have to tell you what this number should be. What is the push forward of the function 1 sub w? and it is defined to be the Euler characteristic of the fiber. Topological Euler characteristic, something that everybody's familiar with. It's not hard to check that this is indeed a functorial prescription. That is, if you compose two proper functions and take the push forward, in a sense, that's the same as composing the push forwards. And there's another covariant functor around, which is homology. This is right because that's what I want you to focus on. Chow is also a nice covariant functor, but pick homology. That's also a functor from varieties to abelian groups. So now you have two functors, two covariant functors from a category to another category, and as mathematicians, you should, or I should, we should ask whether there's a way to connect them. And that's what became known as a question posed by Deline and Grothendieck. Is there a natural transformation that is a system of commutative diagrams, essentially, which links these two functors? So that if V is no singular variety, then the image of the indicator function of V is the Chern class. Questions? You should complain if what I say sounds mysterious. I'm trying to claim that this is a natural question in the context. You have two functors, you have to compare them, and then the genius of these two guys was to require that the simplest function here would go to the most interesting class over there, for non-singular varieties. So this was around for a little while, and then McPherson came around in about 10 years after this was posed and proved that this is indeed the case. So there is such a natural transformation. Yes, please. Yeah. In McPherson's paper, that would be smooth. Would be complex projective varieties, and the theory is being pushed beyond that. For example, Kennedy and others, I'm also partly responsible for that, do this over arbitrary algebraically closed fields of characteristic 0, and even the compactness hypothesis is gone. So we can do this. We don't even need to just look at proper maps. It works for very, very generally. But that's a good question, because since I've been advertising that this should work for non-compact things, I'm kind of doing something a little strange, because this theory is defined on compact varieties at this stage. So please appreciate this. It's a very, this is maybe the main thing in my talk. There exists a functorial theory. Functorial is good, right? Even if you're not used to thinking about functorial all the time, but you are happy if something is functorial, of Chern classes, something that generalizes the familiar notion of Chern class from non-singular varieties, that works for arbitrarily singular projective varieties. It satisfies the same combinatorial properties as the topological Euler characteristic. So it's a powerful observation. This is a beautiful theorem. So now, if you fix a projective, for example, Pn, and then look at any locally closed subset, for example, an affine variety within Pn, it does not need to be compact. Then I can define a class. The class is called the Chern, Schwarz, McPherson class, by assigning to x the value of this natural transformation at the indicator function 1x. Now, the indicator function is the simplest function. Right? This should be a very simple object. It's the most natural choice of a function, and then you have this natural transformation. What could be more natural than that? So this is, don't even know if I'm pointing this out. Probably not, but the point is that if I plug a non-singular variety in place of x, what I get out is the ordinary Chern class of the tangent bundle. So I've managed to find an analog for the Chern class of the tangent bundle, even if the tangent bundle is not there. And here I'm making the point that this can be done actually in Chow, so you don't need to, it's a finite theory in Chow. Okay, so for example, there exists a well-defined class, the Chern-Schwarz-McPherson class of M0n in the homology of M0n bar. And I think nobody knows what the class is. And every now and then I get the idea that I should compute it, but I've never gone very far with that. I think it would be a very interesting object to study. So I want to give you a little bit of a feel for what this class does and how you compute it very quickly. I claim it has the same combinatorial properties as the Euler characteristic. For example, you have inclusion-exclusion. If you have two subvarieties of a fixed variety, then you get this nice, I call it inclusion-exclusion because in the US, when we teach combinatorics to undergraduates, we have this principle of inclusion-exclusion that tells you that the number of elements in the union of two sets is the sum of the elements in here, plus the elements in here minus the elements in the intersection. And you see that's exactly what this class is doing. So there are formulas for this that again call back to the same ingredients that define intersection theory. There's formulas in terms of Chern classes and Z classes for these objects. And in fact, I was able to put together a procedure that runs on Mac OS that will compute this class if you give me the ideal of a subscheme of projective space. So I'm trying to point out that these things can be computed. And they have to do with logarithmic differentials, which you people seem to care about. If you look at the complement of a simple number crossing divisor, then the CSM class of that is the same information as the Chern class of the dual of the logarithmic forms on V. And in fact, this generalizes to more general, not arbitrary, free divisors, the result of also a beautiful theorem. It's not hard to see that if you are within Pn, then the degrees of the components of this class carry the same information. This is not an equal sign because they're not the same, but they have the same information as the Euler characteristic of general linear sections of X. So to some extent, they are geometric objects. Let me give you a hint of why functoriality is so nice. Out of functoriality, you get a Poincare-Hopf. Functoriality means that this kind of diagrams commute. So if you start from a constructible function on V, carry it over to H star, apply this natural transformation for the constant function, you should get some identity. And the identity you get is Poincare-Hopf. If X is non-singular, this is saying that the Euler characteristic of X is the degree of the Chern class of X. But this generalizes Poincare-Hopf to arbitrary singular and arbitrary non-compact varieties. How's my time? I started a little late, so I think I still have a few minutes. Okay, CSM has been studied for decades at this point, very intensely in the last 20 years or so. Paolo have a paper on the Journal of the MS on the CSM class for degeneracy loci. That's an umbrella that covers many, many interesting cases in geometry. Toric varieties are very easy to deal with in terms of CSM class. If you are familiar with toric varieties, each orbit, take the closure of each orbit, that gives you a cycle within the toric variety. Take the sum of those with coefficients 1, that gives you the CSM class. So, what could be simpler than that? And right now, actually, we are working very hard to figure out the theory of CSM classes and more general objects on sugar varieties in flag manifolds, and that's a work in progress to some extent. There have been generalization. There's something called motivic Chern classes. There's the covariant version of CSM classes, and so on and so forth. And this has been very active. Okay, more time for complaints, questions. What I want to do in the next 9 slides, I'm always very happy when the speakers put the number of slides so I know where I am in the talk. In the next 8 minutes and 9 slides, I will say something about graph hypersurfaces, because that's the closest that I've ever come to working with something that sounds a little like what you people are doing. Of course, I'm totally ignorant about the physics side of the story, and I beg for your forgiveness already. But to start with the graph, and the motivation is you want to look at contributions that the graph may give to the computation of a Feynman integral. The edges correspond to variables, and there's a polynomial that you can look at. And I think this is called the Kirchhoff, or the second Zimanzik polynomial. It's a specialization of the Tott polynomial. It's just the sum. You're probably more familiar with this than I. You take the sum over all maximal spanning forests of G, if G is connected just spanning trees, and you take the product of the variables corresponding to edges not in the tree. That gives you a polynomial. For example, here's my favorite case. You start with the banana. The spanning trees, you see them, and there's 1, 2, and 3, and the edges are not in the spanning tree are just choices of 2 of the variables. So, super explicit polynomial. This is homogeneous, and it defines a certain hypersurface in Pn-1, so that's what I call the graph hypersurface. Turns out, actually, it's sometimes better to consider the cone over this in AN, but maybe that will not play a role. The degree is the number of loops in your graph, and this is irreducible if and only if you cannot split the graph as a disjoint union of two graphs. So at some point, we wanted to understand this. And the motivation, again, this is beyond my pay grade to some extent. It's above my head, but there were hundreds of computations suggesting that contributions of graphs to Feynman amplitudes may be very special kind of numbers, and this was mentioned yesterday to some extent. Multiple zeta values. For a while, this was kind of mysterious, I suppose. It had been verified for all graphs up to a tremendous number of edges, but still small by all measures. And it just, at some point, was realized that this was not going to be the case for all graphs. And Francis Brown is about the world expert on this, so he would be the right person to talk about it. In any case, as was mentioned already, the Feynman contribution of a graph is a period of the component of the hypersurface. And these are controlled by the motive of the hypersurface. So what is the motive, by the way? It's some kind of universal error characteristic. We can talk about it, but that would be taking too much time. And in fact, I see my time is running out, so let me accelerate a bit. But I'm still trying to give the motivation. So this fact about multiple zeta values was related to qualities of this motive. It was a conjecture that, for example, if you count the number of points over a finite field of these hypersurfaces, that number should be a polynomial in the number of points in the field. So the question was, is the motive of such a hypersurface, or rather its complement, a so-called mixed state motives? And I just told you that this is actually not true. It was not true. Nevertheless, it generated the questions, right? For which graphs is it true? And what kind of operations on a graph would preserve this property? And more broadly, study properties of a graph which only depend on this hypersurface. At some point, this name was floating around algebra geometric Feynman rules. In a sense, these are just homomorphism from an algebra of graphs to your favorite ring that should only depend on XG. And CSM, this class I talked about, is also a generalized error characteristic. For some reason, it does not depend on the motive, and ask me why if you care. Anyway, this I took as a motivation to study the CSM class of the graph hypersurface. Can be used to construct one of these homomorphisms from graphs to some interesting ring. So number one, and for certain easy graphs, and this is joint work with Matilde Marcoli, whom some of you may know. For simple graphs, this could be computed very explicitly. We don't need to get into that. In any case, I will not tell you anything about the proof. It really relies on the functoriality of CSM classes and constructions that have to do with these hypersurfaces. Maybe the moral here, I think I have a line about that, is that the work needed to compute the motive, which is this high-level object, can be retooled to say something about the CSM class. So in particular, by the way, this is something that you may disprove, you may no more example deny. For these banana graphs, you see the error characteristic is plus or minus 1, right? And you care about the error characteristic of the complement of these kind of hypersurfaces. Sorry, yes. I didn't write it correctly. What I meant was the error characteristic of the complement of the hypersurface corresponding to the graph. So the kind of error characteristic that I've heard you talk about. And I've never seen a graph for which this is not 0 or plus or minus 1. If you know more examples, I think Francis will be the right person to come up with an example that is not the case. All the examples I've been able to compute, the error characteristic of the complement of the hypersurface was always 0 or plus or minus 1. And that's kind of striking cause for a proof if it is true on a contact example. Let me just say a word about a companion algebra geometric Feynman rule. This formula, which if you're like me at the talk you cannot parse, but you can take the CSM class and then cook up a polynomial that has the same information. Well, it is a homomorphism of the algebra of graphs. So it satisfies the basic property that we require of these algebra geometric Feynman rules. Its target is polynomials. This is a polynomial. You can compute it in many cases. The corresponding propagator, if that is the right term, is 1 plus t. And properties of these, I can just list a few. We don't need to stare at all of them. Let's see, it's monic. Coefficient of t minus 1 is easy. Maybe this one is the one that you might care most about. The Euler characteristic of the complement is the first derivative of this polynomial evaluated as 0. So to some extent, this polynomial has some information you may care about. And then you can try and prove theorems about this polynomial, and this is the most sophisticated result I ever got about it, and I'm very unhappy about it, which is why I more or less stopped working on this, because of these unfortunate technical conditions. If you have an edge of a graph, then I have a way to relate the graphs you get by doubling the edge, leaving the edge alone, removing the edge, or contracting the edge. Now, this is a prototype for a deletion contraction formula, which is the kind of things you expect in handling with graphs. But these unfortunate technical conditions are really unfortunate, so that limits the scope of this kind of formulas a lot. But no, there's a hint that this polynomial can actually be computed in practice and satisfy some nice results. Okay, so one question is, can you throw away those conditions? I couldn't, and if you're interested, you can look up my paper and see if you can get rid of them. And there are now natural questions, and my time is definitely up. Can you construct a CSM class in twisted cohomology? Really, this is a question about how functorial is the cohomology you care about. No. Your twisted cohomology, does it have a nice functoriality that they can start from to try to construct a theory of CSM classes in twisted cohomology? And if there's such a theory, then is there a twisted algebraic geometric final rules? And the reason why you would care is that maybe then relations among these classes would correspond to relations of the corresponding amplitudes, which is a speculation without any shred of evidence whatsoever, but it's a question. Okay, so thanks for your attention. Sorry for
Thank you very much for this interesting talk. We have a few moments for questions. One already. You want to go?
What if any are the connections between the CSM or the graph surface and the class and the quantum
yes.
Class and K0.
Yeah, in a sense, let me answer that by why is this not coming from the. So the question is, if this was recorded, whether there's a relation between the class and the Grothendieck ring, which I've not talked about, that is what I hinted at by saying motive, and the CSM class. If there were a nice relation that would allow me to go from one to the other, that would be done. The Grothendieck ring is universal with respect to Euler characteristic, and the CSM class has an Euler characteristic flavor, so you would expect there should be a homomorphism from the Grothendieck ring that determines the CSM class, and that doesn't happen because the universality of the Grothendieck ring refers to Euler characteristic with a fixed target, while the CSM class has moving target. The target of the CSM class is the homology of the variety you're working with, and that moves. So now, there are situations in which you can establish an easy connection. And for example, if you're just dealing with hyperplanar arrangements or arrangements of linear subspaces in projective space, then the information is the same. So for example, I use this to get out of CSM class the chromatic number of a graph, because you can interpret that as the Euler characteristic, more or less, of the complement of the corresponding hyperplanar arrangement. Things like that. But yeah, excellent question, but unfortunately the answer is no.
Okay, so you computed the Euler characteristic of the graph hypersurface, but you took one of there are two graph polynomial you can construct from a Feynman graph, right?
Right. I've only dealt with this polynomial. I've never looked at the other one.
Yeah, so the other one is really where the physics is, because the Euler characteristic counts the number of what we call master integrals. So in particular, the Euler characteristic is non-zero. I mean, is different from 0 and plus or minus 1. I mean, it really knows about the geometry that is beyond that.
That's encouraging me to work on that, or that should be looked at, but I've never worked with it. Sorry.
So, well, you didn't look at this one. Is this for technical reason, or is it? No,
there are many other things that
okay.
My fault. But thanks for suggesting that. Certainly sensible question.
So I wanted to ask about your unfortunate technical assumptions, and my hearing isn't very good, so I didn't hear whether or not it's unfortunate that you had to make technical assumptions to prove it, or unfortunately there are counterexamples? Which is the case?
Oh,
Are there counterexamples?
I think it's the former, but this is work that goes back almost 10 years, and I've tried to forget it to some extent because it was a disappointment. The condition is, in fact, I will not even be able to reproduce it right now, but it is a funny condition that is not always satisfied. The question is whether that condition is necessary for the result, and I don't think I know the answer to this second question.
So
I have counterexamples to the condition, but not to the consequence of the condition.
yeah, right. So
And the condition is, it's kind of funny. It's requiring essentially, oh my goodness, it was easy to state when one remembered it, but it had to do with whether the derivative, the partials of the polynomial that defines the Greif hypersurface would be in the ideal generated by deletions or something like that. So something that seems totally unlikely, and then you try for 5 graphs and it works all the time. And then, no, at the 6th graph you'll find a counterexample. So there are situations in which you can guarantee that that is the case, and that's what led to that.
You see, I want to report this to Karen Yates, who's an expert on the combinatorics of the
yes,
first
Karen Yates has written a
semantic
paper on
thing.
that,
So I want to be able to tell her whether or not there's a counterexample to that as a conjecture.
Karen Yates and a postdoc and a student of hers had a paper on one of these conditions where they studied more carefully than I ever did, and she will be able to answer your question. But I don't know if that is a counterexample to the formula put in the board. That's a different story.
Thank you.
So I don't see any more questions. We can thank Paolo again.
Thank you.